In this place posit video, I'm going to show you how to use Charles' law and or Boyle's law. So we have this problem. The gas in a balloon occupies 2.25 liters. So this is a volume that we're given, 2.25 liters at 298 K. So this is the temperature. So we have a balloon that's full of gas with this volume and this temperature. And we want to know at what temperature will the balloon expand to this volume, 3.50 liters. So the first thing I do is I write down everything that's given to solve this problem. So I have a V1, so a first volume that's equal to 2.25 liters. And I'm also given temperature 1. So this temperature applies to this volume. So I'm going to call this T1. So T1 is equal to 298 Kelvin. The first thing that you're going to want to do before you start solving this problem is to make sure that your temperature is in Kelvin. If it's not, then you need to convert the temperature to Kelvin. Do not plug in temperature into Charles' law or any of the gas laws for that matter in degrees Celsius or degrees Fahrenheit. Your temperature needs to be in Kelvin. Okay, so if it's not, grab a scrap sheet of paper or go to a different slide on your iPad and convert the temperature into Kelvin. In this case, it's already in Kelvin, so we don't have to do anything else. But then we want to know at what temperature will the balloon expand to a second volume, this 3.50 liters. So I'll label that as V2. So V2 is equal to 3.50 liters. Now I do check. Okay, I make sure that my volumes have the same unit. Okay, so if this is in milliliters and that's in liters, then I need to convert the milliliters into liters. I need to make sure that my volumes have the same unit. And in this case, both of my volumes have the same unit, so I don't have to do any conversions there. Now, by just looking at Charles' law and Boyle's law, okay, hopefully it's obvious to you that we need to use Charles' law to solve this problem because we don't have the pressures. In fact, since this problem doesn't say anything about pressure, we can go ahead and assume that the pressure is constant, which is a condition to be able to use Charles' law. So we're going to make the following assumptions. Pressure, in this case, pressure is constant. Okay, even though it's not explicitly stated in this problem, we're going to assume that the pressure is constant. Another variable that we're going to assume is constant are the number of particles. All right, number of particles. It's kind of getting a little tight down there at the bottom, so sorry if you're having trouble reading that, but number of particles also constant. Now, with the given information written down, oh, that's an awful T. Let's redo that. So, constant. Okay. Now, with this given information, I have 2 volumes and 1 temperature. So it's pretty obvious that I need to use Charles' law to solve this problem. So I'm going to plug in the first volume in for V1, the first temperature in for T1, and I'm going to plug in the second volume in for V2. And then our only unknown is going to be the temperature 2, which just happens to be the temperature that the balloon will expand to 3.50 liters. So let's do this on the right-hand side. Plugging in V1 for V1, I get 2.25 liters divided by temperature 1, which is 298 K. So divided by 298 K is equal to, okay, plug in volume 2 for V2, is equal to 3.50 liters divided by T2. So we don't know what that temperature is. That's what we're looking for. Now, since we have two fractions here, I've got a fraction on the left-hand side of my equation and a fraction on the right-hand side. Because these two fractions are separated by an equal sign, I can just cross multiply. Okay, so to cross multiply, I just do T2 times 2.25 liters. So T2 times 2.25 liters, and that's equal to, that's equal to 298 Kelvin times 3.50 liters, which is equal to 1,043, I'm running out of room, so I'm just going to write my units below that number, liters times Kelvin. Now, since I'm running out of space here, I'm going to go to the next slide where I have already rewritten this expression that we've solved for. So I go to the next slide, and here we have temperature 2 times 2.25 liters, which is equal to 1,043 liters times Kelvin. Okay, so hopefully at this point, it's just basic mathematics to be able to solve for temperature 2. So in order to solve for temperature 2, I can see that I'm multiplying the temperature by 2.25, so I have to do the opposite operation, which is dividing, to solve for T2. So I divide this by 2.25 liters, and whatever you do to one side, you have to do to the other, so I divide the other side by 2.25 liters. Now, let's look at the left-hand side. What you can see is that I have 2.25 divided by 2.25. So anything over itself is just 1, so I can just cancel those out. Now, let's look at our units on the left-hand side. I can see that I have liters divided by liters. So again, anything over itself is just 1, so I cancel those units out. So what I have here is T2 on my left-hand side. The temperature that we're solving for is equal to, so 1,043 divided by 2.25. That is approximately 464. I'm just going to round that. So you probably got something like 463.555555 when you type that into your calculator, but I'm just rounding it to 464. Now pay close attention to the units here. Okay, so I already divided these two numbers. Now I have liters divided by liters. Anything over itself is just 1, so my liters cancel, and I'm just left with Kelvin. Okay, so that is my final answer. So let's interpret this. What this means is, once the temperature of this gas reaches approximately 464 Kelvin, the volume of the balloon will expand to 3.50 liters. Okay, so to answer the question, at what temperature will the balloon expand to this volume? The correct answer is 464 Kelvin. I hope you enjoyed this Play Pause It video. Please continue to work through the rest of the worksheet in class, and if you have any questions, just ask.